Hi, I am Wasim, your teacher for analytical mechanics. Today I will solve problem 19 from chapter 4. The statement of the problem is an atom is situated in a simple cubic crystal lattice. If the potential energy of interaction between any two atoms is of the form Cr minus A, where C and A are constants and R is the distance between the two atoms. Show that the total energy of the interaction of a given atom with its six nearest neighbors is approximately that of the three-dimensional harmonic oscillator potential. The potential is V is equal to A plus B into x square plus y square plus z square. In this equation, A and B are the constants. So as it is mentioned that the case is simple cubic crystal lattice. So you know that the simple cubic crystal lattice has six nearest neighbor atoms. So in this uh, problem they mentioned that the nearest neighbor atoms are situated at points plus minus d 0 0, 0 plus minus d 0, 0 0 plus minus d, and the displacement of the situated atom from the equilibrium position like 0 0 0. So the displacement is x y z, and it is given that V is equal to, this V is the potential is equal to summation of Cri minus alpha. Actually, because there are six nearest neighbor atoms, so their position from the situated atom is like R1, R2, R3, R4 and R5. So we have to calculate V1, V2, V3, V4, V5 and V6. Then we will add those potentials and we can get V. So this R1, this is the position of situated atom from the first nearest neighbor, which is situated at D00. So this here R1 is equal to d minus x whole square plus y square plus z square. The whole power is 1 over 2. Similarly, we can calculate R2, R3, R4, R5 and R6. So the simple cubic crystal structure, I believe you have made your understanding in your high school physics. So this is the structure for simple cubic crystal, and these are the nearest neighbor atoms. So this is the equilibrium position, and these are the six nearest neighbor atoms, and suppose they are situated at point plus minus d 0 0, and this is x, one is at the plus x and one is at the negative x, and similarly 0 plus minus d 0, 0 0 plus minus d 0. So these are the six atoms, like plus minus 2 atoms, plus minus 2 atoms and plus minus 2 atoms. So if an atom is situated in a simple cubic crystal lattice, the six nearest neighbor atoms, as I explained in the previous slide, they are situated at these points. The displacement of the given atom from the equilibrium position 0 0 0 is equal to x y z. It is also given. The displacement is very small than d, which is the distance of situated atom from all six nearest neighbor atoms. So suppose we will start from R1. So calculating the situated atom's distance from neighboring atom 1, which is situated at D00. So this R1 is also given in the problem, and as given in the statement of the problem, V is equal to summation of Cri minus alpha, and using the value of R, using the value of this R in this equation, we will get Cr1 minus A is equal to c into d square plus x square minus 2dx. So when we open this square, so we will get these terms, plus y square plus z square whole power minus 0.5 alpha, because this is the minus, so here it comes. So this is r1, so it should be equal to v1 if we see this equation. So v1 is equal to c d square minus 2dx plus x square plus y square plus z square, the whole power is minus 1 over 2 alpha, 1 over 2a. So taking d square common from this equation, this is just the simplification, we will get v1 is equal to cd minus a into 1 minus 2x over d plus x square plus y square plus z square over d square, the whole power is minus 1 over 2a. So using this approximation for small value a, the approximation is 1 plus a, the whole power is n, is equal to 1 plus nx plus n into n minus 1 over 2x square. So when we use this approximation in this equation, we will get v1 is equal to cd minus a into 1 plus minus 0.5a into minus 2x over d plus x square plus y square plus z square over d square plus minus 0.5a into minus 0.5a minus 1 over 2 into 2x over d plus x square plus y square plus z square over d square, the whole power is square. So in this equation, like finally we get this equation. So how we get this equation? Actually we remove the terms which are greater than square. So in this equation, I cannot go in the previous slide. So here you see we remove the terms which were here, so those terms were greater than square, so we simply removed those terms. So now we will calculate the distance of situated atom from neighboring atom 2, which is situated at point minus t00. So in previous case we calculated v1 and we use the value of r1. So now we have to calculate v2 and we will use the value of r2. So r2 means the position of situated atom from the neighboring atom 2, which is situated at this point. So from this point the r2 is equal to minus d minus x whole square plus y square plus z square, the whole power is 1 over 2. So why this is minus? Because the atom is situated on the minus x side, so this d is minus, so that's why this here we get the sign minus sign. So putting the value of r2 in equation, v into v is equal to summation of cri minus a, as we did before, we will get this equation which is equal to v2. So v2 is equal to c into d square plus 2dx plus x square plus y square plus z square, the power is minus 1 over 2a. This minus is because here this is minus a. So taking common d, so we will get, as we did before, v2 is equal to cd minus a into 1 plus 2x over d plus x square plus y square plus z square over d square, the whole power is minus 1 over 2a. Similarly, using the approximation for small a as we used before, we will get v2 is equal to cd minus a into 1 plus into minus 0.5a into 2x over d plus x square plus y square plus z square over d square plus minus 0.5a into minus 0.5a minus 1 over 2 into 2x over d plus x square plus y square plus z square over d square, the whole power square. So this is the term which is greater than square. So we will remove this term and we will simplify these terms. So if we expand the previous equation, we will get V2 is equal to CD minus A into 1 plus minus 0.5 A into 2x over D plus x square plus y square plus z square over d square plus minus 0.5 A into minus 0.5 A minus 1 over 2, and we expanded here the square, which is 2x over d whole square plus x square plus y square plus z square over d square the whole square plus 2 into 2x over d into x square plus y square plus z square over d square. So again we will remove the terms greater than square as I explained in previous slide. We will get V2 is equal to CD minus alpha into 1 plus minus 0.5 alpha 2x over d plus x square plus y square plus z square over d square, this is d square, plus minus 0.5 a into minus 0.5 a minus 1 over 2 into 2x over d whole square. So this is the equation 2. This is V2. So if we carefully see equation 1, this is equation 1 and equation 2, the difference is only the change of sign here. So in V1 this term has negative sign, and in V2 the same term has positive sign. So all the other terms are same. So only the difference is change of sign in V1 and V2. So in order to calculate V, we need to sum up V1, V2, V3, V4, V5 and V6 like this. V is equal to summation of CRI minus A, which is equal to V1 plus V2, V3 plus V4 plus V5 and plus V6. Until now we have calculated V1 and V2. So if we add them, then the relation will be like this: V1 plus V2 is equal to CD minus A into 1 plus minus 0.5 A into minus 2x over D plus x square plus y square plus z square over d square plus minus 0.5 A into minus 0.5 A minus 1 over 2 into 2x over d whole square. The second term is plus CD minus A into 1 plus minus 0.5 A 2x over d plus x square plus y square plus z square over d square plus minus 0.5 A into minus 0.5 A minus 1 over 2x over d whole square. So this is V1 and this is V2, and only difference is sign. So after simplification we will get V1 plus V2 is equal to 2CD minus A into 1 plus minus 0.5 A x square plus y square plus z square over d square plus minus 0.5 A into minus 0.5 A minus 1 over 2 into 2x over d whole square. Similarly, we need to calculate V3, V4, V5 and V6. Until now we have calculated V1 and V2 and we just added them, because for V, for total potential for 6 neighboring atoms, we have to add all the V1, V2, V3, V4, V5 and V6. So for that we need to calculate the distance. Actually, in order to calculate each of these potential like V3, V4, V5, we need to calculate the distance of situated atom from neighboring atoms at points 0 plus minus d0 and 0 0 plus minus d, and at first 2 points we already have calculated. So these are the remaining 4 points. So if we have the value like position vectors, then it is very easy to calculate the value of V3, V4, V5 and V6. So here I mentioned from these points that R3 is equal to x square plus d minus y whole square plus z square, the power is 1 over 2. So this is for point 0 d 0, and r4 is equal to x square plus into minus d minus y whole square plus z square, the whole power is 1 over 2, and this r4 is from the point 0 minus d 0. Similarly, we have the values of r5 and r6 from the point 0 0 plus minus d. Using these r vectors, I want you to calculate the v3, v4, v5 and v6. So I actually, to save time, I already have calculated these, and I will just add v3 and v4. So by adding v3 and v4 and after simplification, we will get 2cd minus a into 1 plus minus 0.5a into x square plus y square plus z square over d square plus minus 0.5a into minus 0.5a minus 1 over 2 into 2y over d whole square. So why there is a y? Because v3 and v4, they belong to the point 0 plus minus d 0. So 0 plus minus d is in the y-axis. So adding v5 and v6, v5 and v6 are from the point 0 0 plus minus d. It means the neighboring atoms we are discussing, they are situated in the z-axis, plus minus z. So here the term is z. So I think you can understand now. For v1 and v2, here the term is x, and for v3 v4 the term is y, and for v5 and v6 the term is z, because the neighboring atoms for v1 and v2 they are situated in x-axis, and for v3 and v4 the neighboring atoms are situated in y-axis, and for v5 and v6 the neighboring atoms are situated in z-axis. In order to calculate v, as I mentioned before, we have to add the equations 3, 4 and 5. So this is the equation 3, equation 4 and equation 5. Simply we are adding, we are going to add v1, v2, v3, v4 and v5 and v6. So I just added those terms here, and after simplifying I mentioned here 2cd minus a into 3. Why there is a 3? Because in equation 3 the term is 1, and in equation 4 this is term 1, and equation 5 that this is the term 1. So when we add 1 1 1, so it is 3. Similarly, because these terms are same, so we are adding 3 equations, so the term here we can get 3. So 3 plus 3 into minus 0.5a into x square plus y square plus z square over d square plus minus 0.5a into minus 0.5a minus 1 over 2 and into 2x over d square from equation 3, 2y over d square like this term plus 2z over d square this term. So only these terms are different, so we added them here. So using these r vectors, I want you so this is the simplified form of this equation, like v is equal to 2cd minus a into 3 plus 3 into minus 0.5a into x square plus y square plus z square over d square plus minus 0.5a into minus 0.5a minus 1 over 2. So is equal to into 4 over d square into x square plus y square plus z square. We only took actually here the common 4 over d square. So taking x square plus y square plus z square as common from the previous equation, so it is more simplified, like v is equal to 2cd minus a into 3 plus x square plus y square plus z square. So these are the remaining terms after taking common. V is equal to 2cd minus a into 3 plus x square plus y square plus z square into 3 into minus 5 minus 0.5a over d square plus 2 0.5a square plus 0.5a over d square. So after simplifying, we will get this term v is equal to cd minus a into 6 plus a square minus a over d square into x square plus y square plus z square. So after defining the constants, like this is the a constant and this is the b constants, we can get the equation, we can get the potential v is equal to a plus b into x square plus y square plus z square. Thank you.